So multiply. So of course we know that any reflection, we already know that any reflection in the group must be of the form rotation to some power multiplied by sigma. So and there should be n distinct such reflections. So of course assume k is not equal to n, and assume that this sigma is distinct, sigma L is distinct from sigma. And multiply it on the right with sigma. So consider sigma L, sigma. On the left doesn't matter. Consider composition. Consider the composition of sigma L with sigma. What can you say? If L does not contain A, then this composition in either order will be, of course, a rotation. We cannot have any translations. It will be even isometry, so must be a rotation, but it will be a rotation about the center, which is not A, since A does not belong to L, and the center must belong to L. So from that it follows, from here it follows that since we cannot have rotation with a different center, since say sigma sigma L or sigma L sigma must be a rotation about A, hence A must be in L, and we conclude that hence any sigma L inside the group must be a reflection in line through the center, through the center of the rotations. That means that our group is exactly, hence it follows that G is one of the dihedral groups, Dm, consisting of n rotations and n reflections. In other words, generated by these two basic isometries. Okay, so thus we have the Leonardo's theorem that any finite isometry, any finite group of isometries must be Cn or Dn. Okay. So remember that we were discussing groups of isometries of polygons. When we were estimating how many isometries can a polygon have. So now we are not assuming that polygon must be that the polygon is a regular polygon. It could be highly irregular. All we care for is that it has a finite number of vertices. In fact, let's consider a polygon with m vertices. So the question is, how many isometries can an m vertex polygon have? Any polygon. And we figured out that since for the first vertex we have m choices for where to go, and the next vertex has to go to some adjacent vertex, and there are two choices for adjacent vertices. So we'll have at most 2m isometries, because after that, after we determine more specifically two m isometries which leave the polygon intact, which fix the polygon, so at most 2m symmetries. And of course it can have less. So after we decide where the first two vertices go, then the rest will be determined. So after that there are no more choices, there is no more freedom, so we have at most 2m symmetries for a m vertex polygon in plane. But what does it mean? It means that any polygon has a finite symmetry group. In fact, no more than 2m, no more than twice the size of the polygon. So the most highly symmetric polygons, the regular polygons, have full size symmetry groups, and others have less. So that means that as a corollary of this theorem, we get the statement that any polygon in plane has a symmetry group. That is Cn or Dn. So notice that now we're talking arbitrary polygons, so m polygon. So that means n here must be, pause and think, have what relation with m? N is bigger than m, can be equal to m, or less than m. So after you come back, it's clear that in fact n must be less than or equal to m. In fact, remember we had this ratchet polygons where we saw which had the group Cn. So our polygon, the ratchet polygon, had twice the number of vertices that we had elements in the group. Okay, so we cannot have that m is bigger than m. But these two cases are possible. So we only can have n is equal to m when we have the perfect symmetrical regular polygon. Okay, so that's as far